Hi everybody, this video will go over section 3 of chapter 4 where we will talk about logarithmic functions. In this video we are going to talk about the logarithm. We're going to talk about solving logarithmic equations, the properties of the logarithmic functions, and also the properties of logarithms in general and how we can exploit them to solve problems. Now in our last class we talked about the exponential function, and here it is. And one of the things that we mentioned is that this function is 1-to-1, and as a consequence it must have an inverse. And so we can go ahead and find that inverse using the four-step approach that we actually learned in 4.1. And the first one is, of course, set the function equal to y, which is already done, and then interchange our values. And if we did, we would have it here. I'm going to rewrite it again. X is equal to a to the y, and then we want to solve for y. In other words, you want to get y by itself outside of the exponent, and we want it to be equal to something. Anything. Some function of x, of course. Okay, unfortunately, that is kind of hard to do. There's no algebraic tool that I can think of that will take the exponent, the y in the exponent, and bring it down into here, or at least we have not been introduced to any algebraic tool. Of course, that's the purpose of this particular section. So what are we going to do? Well, how about if we define a new function? And let's call it, well, let's call it Bob, because I'm Bob and I like that name, so there we go, it's Bob. Okay, we're going to define it as follows. Bob of x is going to be that value y that a must be raised to in order to obtain x. So what is the output of Bob of x going to be for a specific a? It is going to be y such that a raised to the y power is equal to x. That's the definition of our function. Sounds kind of funky, huh? Well, let's look at a couple of examples. Let's suppose that we are going to restrict a to the value of 2. So basically, Bob is this function for the case where a is equal to 2. Well, in that particular case, then Bob, evaluated at 2, is going to be that value of y that 2 must be raised to in order to obtain the number 2. And what value must that be? That must be y is equal to 1. Okay, so this is going to be, so in this case, Bob of 2 will be equal to 1. Okay, well, what about Bob of 16? Well, once again, that is going to be that value of y that 2 must be raised to in order to get 16. In this particular case, Bob of 16 will be equal to 4, because 2 to the 4th is equal to 16. Okay, cool. All right, well, what about Bob evaluated at 1/4? Well, in that's the case, we want Bob, in that case, we want the value of y that 2 must be raised to so that we get the answer of 1/4. And of course, in that particular case, y must be equal to -2, because 2 to the -2 power, 2, is 1/4. Okay, so that's the way that our function works. And does this actually make sense for us? Well, let's evaluate Bob, or let's let f of x be equal to 2 raised to the x power. In that case, then we're going to have the composition of Bob with f of x. That would be Bob of f of x. That would be Bob evaluated at 2 to the x power, and we want the output to be that value of x that value that 2 must be raised to in order to get 2 to the x, which actually happens to be x. So they are indeed inverses, and I'll leave it to you to show that the composition works in the other direction. So this function seems to work. The only bad news is, well, that function's already been defined, and it is called a logarithm. But that kind of gives you an idea where the logarithm comes from. So here is our definition of the logarithm. Let y be any real number, and let x and a be any positive number except where a is not equal to 1. then the equation y is equal to the log base a of x is equivalent to x equals a to the y power. Now, once again, the expression log sub a of x and represents the exponent to which the base a must be raised in order to obtain x. And normally we read this as log base a of x. Once again, based upon how I read that, of course, the number a is the base of the logarithm, and the number x is the argument of the expression, or the argument of the logarithm. Okay, so how does this work for us? Well, this can sort of be illustrated in our first example. Now remember, we have that y equal to the log base a of x is equivalent to x equals a raised to the y power. So in our first example, and actually this is your first two homework problems, we actually want to write both the equivalent logarithmic and exponential forms. So here we have 3 raised to the 4th power is equal to 81. 3 is the base, okay? So we were going to have log base 3, and then this is the argument of the log. This will be 81. And then that is going to be equal to the power that 3 must be raised to get 81, and that would be 4. Okay? Let's take a look at this one right here. Now this is log 1/2 of 8 equals to -3. So -3 is the number that 1/2 must be raised to in order to achieve 8. So 1/2 is the base. You want to write that as that. We need to raise 1/2 to the -3 power, and if we do, we will get 8. So that is the equivalent equation. Similarly over here, our base is 10. So this is going to be log base 10, also known as the common log. Okay, the argument is going to be 10,000, and then 4 is the number that 10 must be raised to in order to achieve 10,000. So that would be 4. Coming over here, once again, we have log base 5, so we're going to have a 5 here. All right, and now we are going to raise this to the -3 power, and if we do, we will have 125. Now for this one, we have log base 12, okay, and our argument is 12, and in order to achieve 12, we need to raise the base to the 1st power to get 12, and there we go. And then finally here we have the log base 6 of 1 is equal to 0. And what does that tell us? Well, once again, our base is 6. We need to raise 6 to the 0th power in order to get a 1. And there you go. That's how you fill that stuff out. And this brings us to our second example. And once again, we are going to basically leverage the property that y is equal to log base a of x is equivalent to a raised to the y power is equal to x. And we're going to use that property to evaluate these logarithms. Okay, so notice here that we have log base 8 of 64. So that means that 8 raised to some power must be equal to 64. Well, what's that 64? What must that power be? Well, that must be 2. So in this case, the log base 8 of 64 is 2. Okay, similarly here, we have 4 must be raised to some power to get 1 over 16. Of course, 4 raised to the negative 1 over 16, that's the 12, 1 over 16. Of course, 4 raised to the -2 power will actually achieve that objective. Again, 1 over 16 is equal to 4 to the -2nd. So this means that this will be equal to -2. Okay, now check this one out here. Here we have kind of a crazy base. The base is 4.56245. And we want to find that value of y that we must raise this base to in order to achieve 1. Well, any base raised to the 0th power will be equal to 1. So this actually is equal to 0. And then finally, we have this equation here. And once again, we want to figure out what 2 must be raised to in order to achieve 16 to the 3/2. So that looks a little daunting. But remember, 16 is nothing more than 2 to the 4th. So this reduces to 2 to the y is equal to 2 to the 4th, all times 3/2. We can then go ahead and use the product rule, and then we will have that 2 to the 4th raised to 3/2 power is going to be equal to 2 to the 4 times 3/2, which by the way is 2 to the 6. And we have 2 to the y is equal to 2 to the 6. Well, if 2 to the y is equal to 2 to the 6, then y must be equal to 6, and that is what our answer would be. We would need to raise 2 to the 6th power to get 16 3/2. We could also use this property to evaluate logarithmic equations. For example, let's take a look at this one right here. We have log base something where the argument is 16 over 9 is going to be equal to -2. Well, what does that mean? Well, the equivalent equation is x raised to the -2 power must be equal to 16 over 19. 16 over 9. Well, if that's the case, then x squared must be equal to 9 over 16. If that's the case, then x can either be plus or minus the square root of these, but since x must be a positive number, we only need to look at the positive square root, and the square root of 9 is 3, the square root of 16 is 4, so it turns out in this particular case x must be equal to 3/4 for part A. What about part B? Well, for here we have 16 raised to the 3/4 power must be equal to x. And once again, this is really nothing more than exploiting the fact that log base A of x being equal to y is equal to a raised to the y power equal to x. They're both the exact same thing, or they're both equivalent. They both have the equivalent equations or the same solutions. So how would you compute this? Well, there are 16 to the 3/4. Well, there's two ways. You can compute 16 cubed and then take the quarter root of that. However, I don't really know what 16 cubed is, so I don't want to try that. There should be a 6 there. Or you can take 16, the 4th root of 16, and raise that to the 3rd power. Well, I know what the 4th root of 16 is. That happens to be 2. So this reduces to 2 cubed, and then this reduces to 8. So it turns out in this case, x is equal to 8. And then finally, we have log base 36 of the square root of 6 must be equal to x. How in the world could we deal with this? Well, this basically says that in writing this using the equivalent equation, we will have that 36 raised to the x power must be equal to the square root of 6. Okay, well, we can write the square root of 6 as 6 to the 1/2 power. We can write 36 as 6 squared. So now we have a common base. This should be an x. I can use the product rule, and then this will become 6 2x, and over here we will have 6 to the 1/2 power. Now, using our property for exponential equations that we had before, if this is equal, then 2x must be equal to 1/2, which means that x must be equal to 1/4. So that is how that works. And this brings us to logarithm functions. What is a logarithm function? Well, it's basically a logarithm expression expressed in functional form. So here it is, and this is the definition for it. Of course, since we have logarithm functions, what we are usually interested in is what they look like, or specifically what their graph looks like. So here is the graph for the logarithm function base 2, log 2 of x. And I also decided to plot the graph for its inverse, which is basically 2 of x, or 2 to the x power. And notice that this is indeed the inverse, and they are indeed symmetric about the equation or the line y is equal to x. Here are the plots for certain critical points. Clearly, if x is equal to 8, then 8 is equal to 2/3, which means the log base 2 of x is 3. If x is equal to 4, well, 4 is equal to 2 squared, so log base 2 of 2 squared is 2, and so on. Notice that this function is continuous and increasing over the entire domain, which, by the way, is from 0 to infinity. Also notice, I forgot to mention this, that the range is the entire real line. So the range is the interval from negative infinity to infinity. Also notice that the y-axis is a vertical asymptote as x approaches 0 from the right. And also notice that this graph passes through 3 important points. The first one is 1/2 -1, or 1 over a -1. Every single logarithm will pass through 1, 0, because any base raised to the 0 power will always be 1. And then, of course, it will also pass through the point a1, because any logarithm evaluated at its base will be equal to 1. Okay, now remember, this is for the case when a is greater than 1. Now we can also have plots for the case where a is less than 1, and they sort of follow the same behavior as the exponential function did, which is basically that they are now decreasing over the entire domain. They are still continuous, they are still decreasing, the domain is still the same, the range is still the same. The only difference is that they are decreasing. Now, I plotted this with their inverse, with its inverse, which is basically 1/2 raised to the x power. And one of the things that you will notice is that they intersect, which is kind of interesting. And they intersect when they're both equal to each other. But they are also still symmetric about y, even though they have this intersection thing going on. Notice that xy for this particular on this particular graph is going to be yx on the other particular graph. So here we for here we have 0.51, and over here we have 0.5. Or we have 0.252, and here we have 0.25. So we still have symmetry about the line x is equal to y. And of course, once again, this graph passes through the points 1 over a, -1, since a is 1/2, 1 over a is 2. It still passes through the point 1, 0, and it still passes through the point a, which is 1/2, 1, which is right there. Okay, so a number of your homework problems is going to be choosing the correct graph for the following function. So here we have log of 1/3 x. The base is between 0 and 1. As a consequence, this function is always going to be decreasing, just like this function is. Okay, well, this function right here is, and also in MML, you don't really have to plot this, although I would encourage you to actually plot this up by hand a couple of times. But what you will do is you'll be given a collection of graphs, and you have to decide which one is correct. Now, since this is since the graph of this function should be decreasing, we know that this cannot be the graph and this cannot be the graph because they are both increasing. So we're left with these two. The other thing that we know is that the domain is basically all positive values of x, or the open interval between 0 and infinity. Well, this one takes on negative values of x, so this is also not this can also be ruled out, and this is the graph that we are interested in, or this is the graph that represents this function. Now, we can talk about these other graphs because they are actually really nothing more than reflections of this particular graph. For example, this one right here is f evaluated -x. It's a reflection across the y-axis. This one is really nothing more than negative f of x. It's reflection across the x-axis. And this one is negative f of negative x, which is reflection across both the x and the y-axis. Okay, the next one we have here is the log base 4 of x. So for this particular case, the base is greater than 1, which means we're going to have an increasing function, which means that this one's out because it's decreasing, and this one's out because it's decreasing. And once again, the domain has to be all real values of x, or the positive real line from 0 to infinity. This takes on negative values, so this has to be out. This is our logarithm function. Once again, these are just the other functions are just reflections of the logarithm of log base 4 of x. This one is actually negative f of negative x. This one right here is f of negative x. I had to give it a look for a second. And then this one right here is basically negative f of x. Once again, they're just reflections. Now, a couple of your homework problems will deal with translations of functions. And this kind of shows you the question and the answer for the entire for the entire example. However, in MML, what you will have to do is you'll have a little tool. When you click on the graph, it'll plot the function, and a menu will show up, which will give you the opportunity to add the required shift, horizontal shift and vertical shift, and you would need to put in the correct numbers. For this particular problem, we have f of x being equal to log base 2 of x minus 3 plus 2. So the base function is log base 2 of x. The x minus 3 implies a horizontal shift to the right 3 units. And there it is, 1, 2, 3 for our anchor point, which is basically 1, 0. And then the plus 2 here corresponds to a vertical shift up by 2, which would put this point right here and produces for us this graph. Now, once this is all done, you're going to be asked, at least in your homework, where the domain and what the domain and the range are. Well, this will be the domain. Since we actually shifted to the right by 3 or by positive 3, your domain will change from 0 to infinity to 3 to infinity. What about the range? What about the range? Well, it still includes all points on the real line. However, do notice that the vertical asymptote has changed. Now, vertical asymptote becomes is now y equals 3, because as y approaches 3 from as x approaches 3 from above, y will get smaller and smaller and will approach infinity. Okay, the next thing that we want to talk about are properties of logarithms, and I believe you may have seen these before, but we're going to go through them again. These are actually very useful in manipulating problems and simplifying logarithmic expressions. And even in the olden days, before calculators, we would actually use logs and slide rule. We would use logs along with slide rules to compute values for very complicated multiplications. So here we have the log base a of xy, of the product of x and y. And it turns out that the logarithm of a product is going to be equal to the sum of the logarithms of each term. The log base a of x times y is equal to log of x plus log of y. Similarly, from this we can also get the quotient property, and that tells us that the log base a of x divided by y is equal to log base a of x minus log base a of y. So the logarithm of the quotient is equal to the difference of the logarithms. And then next we have the power property. And the power property says that the log base a of the log base a of x raised to the rth power can be rewritten as r times the log base a of x. And this says that the logarithm of the number raised to a power is equal to the power multiplied by the logarithm of that number. And this one we can actually prove. So if the log of base a of x raised to the r power is equal to y, that implies that a raised to the y power is equal to x raised to the r power. All right, now what I can do is I can raise each side to the 1 over rth power. So 1 over r here, and then 1 over r here. And then using our power rule with exponents, we would have that a to the y over r is equal to x. Well, if that's the case, then that would imply that the log base a of y over of x is equal to y over r. And then solving for y, we would have that y is equal to r log base a of x. Okay, so we have an expression for y here, an expression for y here. That implies that these two terms are equal, and that gives us our desired result, which is that the log base a of x raised to the rth power is nothing more than r times the log base a of x. So that's how that can be proved. And then the other two examples are the logarithm of 1 will always be 0, and the logarithm base a of a will always be equal to 1. And once again, we can actually use these to simplify problems or to condense problems. Okay, so here are some examples of things that we can simplify. And the first one is log base a of r times s divided by t. And for this one, we are going to use the product property and the quotient property. Basically, we can use the product property to rewrite the numerator as log base a of r plus log base a of s. And then the quotient property will basically, and we can use the quotient property to write minus log base a of t. And that's it. The product property for these two, and then the quotient property for this. What about b? Well, here we can write this using the product and quotient properties as log base a of r to the fifth plus log base a of s minus log base a of t cubed. Then we can use the power property to simplify this expression and this expression, and that would give us 5 log base a of r plus log base a of s minus 3 times log base a of t, and that would be our answer for this particular one. Now this one, we already have a 1/2 here. So I would rewrite this once again using the power rule, because this is really nothing more than this expression raised to the 1/2. So that would be 1/2 times the log base a of r to the fifth times s divided by t cubed, which we've actually computed right here. So I can just substitute this in for all of that, and if I did, I will have 1/2 times the quantity 5 log base a of r plus log base a of s minus 3 times log base a of t. And that would be our answer for that particular problem. Now, the other thing that you're going to be asked to do is to write the following expression, such as this, as a single logarithm with a coefficient of 1. And what they mean when they say a logarithm with a coefficient of 1, essentially you can't have a 5 in front of the log, or a 3 in front of the log, or in this case a 3 or a 2 in front of the log. So how would you do this? Well, the first thing you would do is you would deal with these terms using the power rule. And if we did, we could write this as log base 4 minus log base 4 evaluated at y cubed plus log base 4 evaluated at z squared. Okay, cool. Now we can use the product rule and the quotient rule. With these, we will have, this should be an x here, sorry about that, log base 4 x over y cubed, that's these two, and then plus log base 4 of z squared. And then we can add this in here, and if we did, we would have our desired result, which is log base 4 x times y, x over y cubed times z squared. Or if I wanted to, I could write this as log base 4 x z squared over y cubed, which would be the answer that we would want to put into MML. Now you can also use these properties to evaluate certain logarithms without using a calculator, which is what we have here. So here we have the log base 10 of 49, and all we know is that the log base 10 of 7 is 0.08451, and we're not allowed to use our calculator. Okay, so I can rewrite this as the log base 10 of 7 squared, because 49 is 7 squared. I could have also rewritten this as log base 10 of 7 times 7. It doesn't really particularly matter. And then this is going to be equal to, using our power rule, or power property, 2 times the log base 10 of 7, which will be equal to 2 times the log base 10 of 7 is 0.8451. And then 0.8451 times 2 is going to be 2. 2 times 5 is 0, carry the 1. This is 9, and then here we have 1.6. So this would be equal to 1.6902. And then for this one, how would we handle this one? Well, we can rewrite this as the log base 10 of 10 times 7. That will be equal to the log base 10 of 10 plus the log base 10 of 7. Log base 10 of 10 is 1, based upon this property right here. The log base of 7 is given for us right here. It's just 0.8451. When you add them together, you get 1.8451. And there you go. Mission accomplished. Okay, and the very last thing that we want to talk about is the great logarithmic inverse theorem. Now that's just really what I called it. We just call it the theorem on inverses. So what does it say? It says that for any a greater than 0, a not being equal to 1, because then we have that the a raised to the log base a of x power of x is equal to x. And similarly, and that really is nothing more than the composition of a to the x with log of x. Okay, and notice that this is only applies for the case where x is greater than 0, because that is the domain of the logarithm. And similarly, log base a evaluated a to the x, which is the composition of log of x, log base a of x, I'm sorry, with a of x is equal to x. So that this is basically showing us that the composition in both directions is equal to x, which is what we're looking for. And we can actually use this to solve a certain problem, a couple of problems that you'll find in your homework. And here's one example of it. Here we want to write an equation for the inverse of the function for the following one-to-one function. And to do this, we need to apply this particular theorem at the appropriate time. Well, once again, to do this, we're going to use the four-step approach that we used in section 1. First, we're going to replace the f of x with y. And that will give us y is equal to 9 to the x plus 6. Then we're going to interchange x and y. And if we do, then we're going to have x is equal to 9 to the y plus 6. And now we are going to solve for y, and we're going to use the inverse theorem as a tool to solve for y. First, we're going to get the y term by itself, and that would basically be 9y is equal to x plus 6. And then we are going to apply this. Okay, we're going to take, specifically, we are going to take the logarithm of both sides, and that will give us the logarithm of the log base 9 of 9 raised to the y-th power is going to be equal to the logarithm base 9 of x plus 6. Okay, well, what is this? Well, once again, that's just y. And then over here, we have the log base 9 of evaluated at x plus 6. We can replace the y with f negative 1. You don't really need to do this in MML. I'm just doing it because it's fun. And that will be equal to log base 9 x plus 6. And that is all I have for this particular talk, or for this particular section. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.